This is Lab 1, Constant Velocity. The main purpose is to apply Newton's laws of motion to the real world. Newton's first law of motion states that an object in motion will stay in motion unless it acted on by an unbalanced force. Newton's second law of motion is presented here, where force is equal to mass, which should remain constant, times acceleration, which should be zero if there's no unbalanced forces. Thus, the net force should equal zero. The experiment today involves the motion of one mass in one direction at a constant velocity and no acceleration. We'll see just how well this fundamental principle predicts the rolling of a basketball. Over here we have our rolling basketball video loaded into Tracker. The rolling ball is the system and everything else is the surroundings. The ball's motion is analyzed a bit after it's pushed and a bit before the ball comes to a stop to ensure a constant velocity. The coordinate system is defined as 0 is the center of the ball and the ball is moving in the positive x direction. This data is then loaded into our computational model. We first have to make a few assumptions. For one, there's no external forces on the system such that the net force does not equal 0, for example the friction force. This could be exemplified in a few discrepancies presented later, but that will be described in future slides. For the computational model, from Tracker we get the initial position, and then we get the position after one time step, which is 0.017 seconds, the frame rate of the camera. We then can calculate the initial velocity using the velocity average formula and get 0.638 meters per second. In this diagram here we can see that whether it is 0.017 seconds or 1.1 seconds, with Newton's second law of motion, this ball should remain at a constant velocity since there's no added force. Now the computational model, the code. We set the ball's mass equal to the ball's mass, and then the ball's position vector is taken from the data in Tracker. The velocity vector is what we just calculated on the previous slide. Then we initialize the time equal to 0, and the delta t is set to a smaller size than the frame rate of the video, and this will allow a better iterative approach for the computational model. Then we start this while loop where t will iterate up to 1.1 seconds, which is the time of the observed model. Then we set the net force equal to 0, and this is due to the velocity update formula of Newton's second law of motion, where if the net force is equal to 0, then the velocity will remain constant. In our system, the velocity remains constant. And here we have the momentum principle where the velocity should update, similar to this velocity update formula, but since the velocity is 0, the velocity will remain the same. The position is updated using the ball's velocity times the change of time. Now we have our computational model, and as you can see, it will very closely identified to the model, the observed model. Then we take this data from our computational model and create a graph. So over here we have a position versus time graph of the model versus the experimental data. We see it follows very closely until about 0.6 seconds, and this discrepancy can be highlighted for two reasons. For one, the deformities of the ball could have caused a slowdown of the change in velocity. Additionally, the friction force from the ground could also affect the velocity, which causes it to slow down, as you can see right here. Some ways to fix this is by having a smoother ball for the experiment or having a smoother floor to ensure a lesser friction force. Also, taking a look at the graph here, we have the origin set as 0, we said the center of the ball, and it's moving in the positive x direction. Now, what if we flip the axis and we swap the positive x with the negative x direction? So over here we have, this is what the positive x looked like, our original graph, and this is what the negative x direction would look like. The absolute value of the slope remains the same, but simply the object moves in the negative x direction. Now, what does this mean? As discussed before, the net force of the system is equal to 0. However, this does not mean that there's no forces acting on the system. With the nature of this experiment, it's hard to say exactly how many pushes and pulls kept the velocity constant. For example, we have the gravity force. We do have the normal force also pushing up from the bottom. But with the velocity remaining constant, we can say that the net force of the system is equal to 0.